Chapter 6, Chemical Equilibrium. Section 6.5, Expressions of Equilibrium Constants. The equilibrium constant of a reaction that involves only ideal gases can be expressed in terms of the pressures, the concentrations, or the mole fractions of those ideal gases. Here's the example. In this reaction, A and B are reactants, X and Y are products. Nu sub A, nu sub B, nu sub X, nu sub Y are coefficients. Now we can express this equilibrium constant in terms of pressures. So over here you have products on top, reactants on the bottom. And we have Px over P naught. This is dependent on the pressure of X. Over here Py over P naught. This is partial pressure of Y over P naught. And then the partial pressures of A and B, the reactants, are on the bottom. We also need to take care of the coefficients in front of AB and XY correspondingly. And this is the definition of the equilibrium constant of pressures, because you see the partial pressures of the chemicals in the final expression. Now we can have this equilibrium constant of concentrations as well. This is just because for ideal gases, somehow we can also use the mole of X divided by the entire volume of the system to get the concentration of X. And then we use the concentration of X divided by C naught. And over here we have one of the two products on top, and the other products also on top, reactants on the bottom. And when we write this, we have the equilibrium constant of concentrations. And again, we have to specify this is equilibrium. That means when the reaction reaches equilibrium, and then we plug in the actual concentrations of X and Y here, A and B here. We take care of the stoichiometric coefficients, and then we'll get the value of this equilibrium constant of concentrations. And finally, we can also express the equilibrium constant in terms of mole fractions. Let's say we have these four gases in the reaction system, and then we have mole fraction of X, Y, A, and B. The sum should be 1. Now, how do we compute the mole fraction of X? Well, it's pretty simple. We need to get the total number of moles of all gases. Let's say denoted by N, and over here it's just the number of moles of X over N. We get the mole fraction of X. This mole fraction of Y is the number of moles of Y divided by the total number of moles N, and then we get the mole fraction of Y. Similarly, we get the mole fraction of A and B. And again, if this reaction system contains only these four ideal gases, the sum of the four mole fractions should be 1. One more thing, not only this mole fraction of X can be computed by the number of X over the total number of moles, we can also use this. The mole fraction of X is also equal to the partial pressure of X divided by the total pressure. And why is that? It's just because for ideal gas we have PV equals nRT. So the partial pressure of X times V is equal to the number of moles of X times RT. And now we see the pressure is proportional to the number of moles for X, and also for Y, and for A, and for B. And all four ideal gases, they have the same temperature, they have the same volume, therefore we have this relationship. P sub X over P is just the mole fraction of X. Again, P of X over P is equal to N of X over N, and N of X over N is just the mole fraction of X. So we can rewrite the equilibrium constant of mole fractions this way as well. It's the same. These two can be proven the same. Now if you pay attention, this expression looks similar to this one, but they're different. Because over here on the bottom we have P, the total pressure of the system. And over here we have P naught, the standard state, the standard pressure, which is just 1 bar. And over here again, this P is often different from 1 bar. Now for this reaction that involves only ideal gases, we can get a relationship between this equilibrium constant of pressures and the equilibrium constant of concentrations. So we write this expression of K sub P on top, This is the K sub C on the bottom. Again, pay attention over here. The standard state is 1 bar on top, the standard state is 1 molar on the bottom. So we do this division, and also we notice that we can somehow combine all the x terms. So we have this term divided by this term, the y term divided by y term, a term divided by a term, b term divided by b term. So we get this expression. And over here, let's just look at x. It's p of x, the partial pressure of x, times c naught divided by c of x divided by p naught. It's just because we have px over p naught over here, and then divided by cx over c naught. So we flip this too. And same for y, same for a, same for b. So we have this awfully complicated expression. We have 1, 2, 3, 4. We have kind of 1, 2, 3, 4, 4 terms just for x, 4 terms y, 4 terms for a, and 4 terms for b. But we can somehow get a general expression. So for just any ideal gas species I, we will do this. We'll do p sub I times c naught divided by c sub I over p naught. First, realize this is unitless because pi over p naught is unitless, c naught over ci is unitless. And now c sub I is the number of moles of I over v, right? That's the concentration, the number of moles over the volume. So we can rewrite c sub I as n sub I over volume. And then we can flip this v up, so we have this expression. Now p sub I times v, what is that? Well, pv equals RT. Alright, you can use PV equals RT for the entire system. Also, you can use P sub I times V is N sub I times RT. So this equation holds true as well for species I. The reason we do this is because now Ni and Ni cancel. We have this C naught RT over P naught. What is C naught? C naught is 1 mole per liter. That's C naught. It's just chosen to be the standard state, as concentration. It's 1 mole per liter. R is ideal gas constant, T is temperature, P naught is 1 bar. Alright, P naught is 1 bar. 1 bar is just chosen to be the standard pressure. And now we have this equation. Alright, Kp over Kc is this. C naught RT over P naught to the power of nu sub x plus nu sub y on top, and then minus nu sub A minus nu sub B because they're on the bottom. So we have this. Now we define delta nu. Delta nu is the change of the coefficient in the reaction, and this is just the coefficients in front of the products minus the coefficients of the reactants over here. And then over here we have C naught RT over P naught. Given the temperature, we should be able to calculate this. Given delta nu, we should be able to calculate Kp over Kc. The ratio between Kp and Kc depends on the temperature, as you can see temperature here, and also depends on delta nu. Again, delta nu is the change of the stoichiometric coefficients in this chemical reaction. And in this chemical reaction, remember, we have only ideal gases. And now we have nu sub x plus nu sub y minus nu sub A minus nu sub B. Now let's look at one numerical example. Let's calculate K sub P over K sub C for this chemical reaction. This is equilibrium constant of pressures. This is equilibrium constant of concentrations. We're going to compute the ratio at room temperature and 500 Kelvin. So first, room temperature. So first, K sub P over K sub C is this, and delta nu is 2 minus 1, so we have this equation. And now we have just C naught RT over P naught to the power of 1, so it's just right here. We plug in all the numbers. Again, C naught is 1 mole per liter by definition. P naught is 1 bar by definition. We plug in R, we plug in the temperature over here. Just pay attention, this liter is 10 to the power of -3 cubic meter, and 1 bar is 10 to the power of 5 pascals. So after you do all those unit conversions, we'll be able to get 24.79. And at a different temperature, we get different value, only because K sub P over K sub C depends on temperature. Now if temperature is 500 Kelvin, we get 41.57. Now let's look at example problem 6.5.2. We can calculate K sub B for over K sub C for any chemical reactions that involve ideal gases. So here's another example from N2H2 to ammonia at room temperature. In this case, first let's look at delta nu, which is 2 minus 3 minus 1, so over here, and then it's C naught times RT over P naught can be easily computed. And we did the calculation over here. We can just borrow this number, we put it in here. It's going to be 24.79 to the power of -2. K sub P over K sub C is 0.0016 for this chemical reaction at room temperature. Again, this K sub P over K sub C depends on temperature and depends on delta nu. However, sometimes if just by coincidence this delta nu is 0, and then, well, K sub P is equal to K sub C by coincidence, when the coefficients of reactants is equal to the sum of the coefficients of the products. Again, for the same reaction from A plus B to X and Y, and we have this relationship between K sub P and K sub X now. First, K sub P is written this way, and then K sub X. Supposedly it's the mole fractions, but the mole fraction of X is the partial pressure of X over P. The mole fraction of Y is partial pressure of Y over P. So we're plugging all those numbers, and then somehow this Px and this Px cancel. So on top you have Px to the power of nu x, and on the bottom you have Px to the power of nu x. So that's nice. And then we can just clean up this expression. We have this P here on the bottom, but you know it's 1 over P appears in the denominator, so we flip this up and then we get this expression. Alright, so it's P over P naught times nu sub x on top, P over P naught to the power of nu sub y on top. And overall we can combine everything. It's going to be P over P naught to the power of delta nu. What's delta nu? Again, it's just nu x plus nu y minus nu a minus nu b. Nu is the stoichiometric coefficient. Delta nu is the change of the stoichiometric coefficients over here, and P is the pressure of the system, and actually it is the total pressure of all ideal gases involved in this reaction, because the pressure of the entire system is the sum of the partial pressures of these 4 species. And again, you know, we have this simple relationship between K sub P and K sub X. If you know the total system pressure, just plug it in here, and if you know delta nu, plug it in here. We will be able to get the relationship between K sub P and K sub X. And again, both K sub P and K sub X are unitless. You can look at this. This is unitless because every single term is unitless. On the bottom, anyway, mole fraction is unitless. Again, these two differ by a factor of this, so somehow you can compute this and you find how K sub P relates to K sub X. Now let's imagine a scenario. What if the volume of this reaction is compressed to only 1/2 of its initial volume? What will happen? Its reaction quotient of pressures will change. Why is that? Well, if you change the volume under constant temperature condition, the pressure will change. If you compress the volume, so it becomes 1/2 of its initial volume, that means the pressure of every single species is doubled. Okay, again, the pressure of every single species, A, B, X, Y, okay, are doubled. That's why the new reaction quotient of pressures will change. So this is the new reaction quotient of pressures when you compress the system to only 1/2 of its volume. This is going to be the initial Q sub P times 2 to the power of delta nu. Why 2 to the power of delta nu? Again, you know, for every single species, its partial pressure is doubled. So that's why we have 2 here. And also in the expression of reaction quotient, we need to take care of the coefficients nu sub x, nu sub y on top, nu sub a, nu sub b on the bottom. So you're going to see 2 to the power of nu sub x, 2 to the power of nu sub y, and then 2 to the power of nu sub a, 2 to the power of nu sub b on the bottom. That's why we have the new reaction quotient of pressures being changed to this. This is the initial reaction quotient of pressures times 2 to the power of delta nu. Again, the partial pressures of all gases are doubled. Meanwhile, the quotient of mole fractions remain unchanged. That's strange, but remember, when you kind of shrink the volume, you're indeed actually changing the partial pressures, right? But also you're changing the total pressure. So the ratio between the partial pressure over the total pressure remains the same. So it's not going to change the mole fraction of any species. That's why Q sub P will change, but Q sub X remain unchanged. All right. Know that K sub P is equal to K sub X under two different conditions. If you have P equilibrium, at equilibrium, if the total pressure happens to be P naught, if this P at equilibrium happens to be P naught, you're looking at 1 to the power of something, and then K sub P is equal to K sub X. Another scenario, just when this delta nu happens to be 0, that means it happens the sum of nu x, nu y is equal to the sum of nu a and nu b, and then we have something to the power of 0, it's also 1. So under these two conditions, either one of these two conditions, K sub P is equal to K sub X. Alright, again, given the final pressure of the system at equilibrium and given delta nu, we can easily compute the ratio between K sub P and K sub X. Now, what if a reaction involves both gases and aqueous solutions? How do we write out the equilibrium constant? Now, we do not call the equilibrium constant, as equilibrium constant of pressures or concentrations, because you have both gases and aqueous solutions. Usually, we use 1 bar as the standard state for gases. We use 1 molar as the standard state for the solute in the aqueous solution. So it's going to be a hybrid expression. Alright, so again, we use P naught, which is 1 bar, as the standard state for the gases, C naught, which is 1 molar, as the standard state for the solutes in the aqueous solution. Again, this equilibrium constant must be unitless, and notice this, we do not have any subscript here. We talked about K sub P, K sub X, and K sub C, but right here it's just K. It's just K. Again, for this reaction, but with some changes. Now this B is solute in aqueous solution. This Y is also in aqueous solution. Now, how do we express this equilibrium constant, this K? K is, again, products on top, reactants on the bottom. You take care of the coefficients appropriately. And now, let's look at X. X is a gas, so it's Px over P naught. Let's look at Y. Y is the solute in a aqueous solution, so it's C sub Y over C naught. A is a gas, and then B is a solute in the solution, so this is C sub B over C naught. And over here we see concentrations, we see partial pressures. That's why we have just a K here that denotes the equilibrium constant. It's neither equilibrium constant of pressures nor equilibrium constant of concentrations. Alright, some reactions involve pure liquids, pure solids. In that case, for example, if you have like pure water, and you are looking at the decomposition of pure water into H plus and OH minus in water, and then you may assume this water is pure liquid water. Its concentration is considered 1. Alright, actually, we're using the mole fraction of pure liquid and pure solid, which is just 1. And now we have this kind of expression for equilibrium constant. So let's say B is a pure liquid, Y is a pure solid. Alright, and for B it's just 1. For this Y it's also 1. Okay, again, Y is pure solid, B is pure liquid, so they're just 1. Now we also have X in an aqueous solution. That's why we use the concentration of X over C naught on top. A is a gas, so we use PA over P naught on the bottom. Alright, again, the concentration, double quoted concentration of a pure solid or liquid is 1, only because the pure solid or liquid with X equals 1 is chosen to be the standard state for the solid or liquid. Okay, so there's a reason. It's just because the pressure dependence of the Gibbs energy of a solid or liquid is typically negligible. So if you have, for example, the standard Gibbs energy of formation of pure water and the standard Gibbs energy of formation for pure gold, you can use the same values under different pressures, like 2 bars, 5 bars, even 10 bars. There's not much change to the standard Gibbs energy of formation for that pure water or pure gold.